Hello and welcome to the first tutorial on the Stat 110 lecture series. Today we're going to be looking at the Strategic Practice Problem Sheet 1, question 1, on the naive definition of probability. Now, as you can tell from my very snazzy hat, I'm a doctor and so I should have no problem helping you with this. Okay, so to start off with, let's just go over what the naive definition of probability is so we're all on the same page. So the naive definition of probability states, say we have some event A and we want to know its probability. Then the probability of that event is the size of the set A, the cardinality of the set A, over the cardinality of the set S. So A is the event, and inside the set of A are all the outcomes that lead to A. Okay. S is called the sample space, and this is the total number of outcomes. Okay. Now, I'm going to assume that you already know a bit of set theory, and so I'm not going to cover that here, but there is another video that I will do on set theory, on the basics of set theory that you need for probability, so you can watch that one if you want to. So, this is the basic idea, and it's based on two things. The first thing is that all the outcomes that are possible are equal probability. And the second thing is that there are a finite number of occurrences. Now, it's actually these two things that make this definition of probability hopelessly naive. Because most of the time, events don't have equal probability. Outcomes don't have equal probability. And frequently, there are not a finite number of occurrences either. So this whole idea is actually based on counting. And the reason it came about is because there were gamblers in the 17th century and they wanted to know how likely are you to win a game given the game's current state. And so that led some French mathematicians to look into this problem and come up with the idea of counting outcomes. Now, because things like card games and dice games are supposed to be fair, you can use this naive definition, and that's what it was originally intended for. So let's move on to the questions. The first question, the first part of question 1, is the probability that the total after rolling 4 fair dice is 21 equal to, less than, or greater than the probability that the total after rolling 4 fair dice is 22? Okay, so if we look here, we can see that we've got these 4 fair dice. Now, it's the fact that they're fair that means we can use the naive definition of probability here. So how do you solve this? Well, the way you solve it is by counting the number of ways 4 dice could come together to produce 21, and then checking that versus the total number of ways that you could get 4 dice to come up with anything. So let's see. So could I have 5, 5, 5? No, that would be 20. So I'm going to need at least one 6. So let's say I've got 6. And now maybe I want 5. That gives me 11, 16, 21. Okay, how many ways are there to do that? Well, via combinatorics, the fast answer is there are this many ways to do it. 4 factorial over 3 factorial ways. Okay. Now, the general formula for this is if I have n elements in a set, then it's n factorial divided by the number of repeat elements. Okay, so in this case, we would say r factorial. And here you can see that n is equal to 4 in this case, and r is equal to 3, because there are 3 repeated 5s. Now, another one could be 6, 6, 5, 5. Now in this case, we've got 4 factorial again, because we have n elements, 4. But now we have 2 factorial times 2 factorial. And that's because I've got 2 elements repeated twice. So this one's 2 factorial and this one's 2 factorial. Okay, so that extends the formula. This is the more general formula. R1 factorial times ... rk factorial. And this is the repeats for repeated element 1. So in this case 6. And the repeats for repeated element k, which in this case is only 5, but it could go up to an arbitrary number, hence the k. Okay, now, a bit magical. You haven't seen why it works, so I'll show you how it works. So say, for example, in the case of 6, 5, 5, 5, if you imagine that the dice are rolled and they all come down one after the other, so they come down in an order, you could say that I could either get first to 6 or first to 5. Okay, well, if I get 6 first, then what else can I roll? Well, it has to be a 5, and it has to be a 5, and it has to be a 5. For the case where I'm getting 6, 5, 5, 5, my 5s look like S's. Yeah? Now, if I roll a 5 first, well, then now I could get a 6 or I could get a 5. And then in this case, I would have a 5 and a 5. And in this case, I would have a 5 and... Oops. In this case, I would have a 6 or a 5. Then I would have a 5 or then I would have a 6. So you can see at the end here, I have got 1, 2, 3, 4 paths that I could take. Okay. Now let's have a look at what 4 factorial divided by 3 factorial is. Well, we know that actually this is just equal to 4 times 3 factorial, and that's over 3 factorial. So those cancel and we get 4 as well. Fantastic. If you'd like another example, you could try it on 6655 yourself, and you'll see that the answer comes out to 24 over 4 equals 6. Okay, so this is how you would solve this problem. Now, I'm just going to take all of this as you understand that now, or you can see how it works, and I'm going to continue. Okay, so wasn't very clear, but this one is in the case of 21, and this one is in the case of 22. Not that it matters that much, it's just about showing you how the formula works. Okay, so let's continue with just 21. So we've got our first one, 6, 5, 5, 5. Next one that we could have. We could have a 6. We could have a 6. We could have a 5, and we can steal 1 from this 5. Okay. So now instead, what have we got? So we've got n again is 4 factorial, divided by these are repeated. So over 2 factorial. So that means we have 24 divided by 2, and that means we have 12. Okay. Next one. 6, 6. I'm going to have another 6 and a 3. Okay. So 4 factorial over 3 factorial again, And then this is equal to 24 over 6 equals 4. So in the end, we end up with 20 ways. Great. So let's note that somewhere. So we have for 21, there were 20 ways. Hooray. Let's do it for 22 now. Same thing, can't start on a 5, have to start on a 6. Can't have 3 5s, so I have to do a 6. Now I've got 5 5, and as we saw before, that's equal to 4 factorial over 2 factorial times by 2 factorial, which is equal to 6. Okay, so 24 over 4, 6. Now, last one we could have 6, 6, 6, 4. There are no others. So this is 4 factorial over, pause the video and guess, 3 factorial. I'm sure you got it right. So that means there are 4. So 6 plus 4, 10 ways. And that gives us our answer because there are 10 ways to get 22 and 20 ways to get 21. And there are 6 of the 4 possible combinations for all of them. So the 20 would be over 6 to the 4. And so would the 10. Okay, so that doesn't matter. It's just the number of ways. So that gives us our first answer. Turns out that in this case, this probability is greater. Hooray! Okay, let's move on to the second question. So now we have part B, and that asks us, is the probability that a random 2-letter word is a palindrome equal to, less than, or greater than the probability that a random 3-letter word is a palindrome? And in case you don't know, palindrome just means a word is the same backwards as it is forwards. So, for example, like AA would be a palindrome because if I reversed those, I would still have AA. Or, you know, ABA, reverse. In fact, better example is probably, I don't know. There we go. Prob-borp. It's the same forwards as it is backwards. Okay, so that's a palindrome. Now the question is, what's the probability that we get a 2-letter word palindrome? And what's the probability that we get a 3-letter word palindrome? Okay. So let's start with the 2-letter case. This 1 here, he's got a 1 here. And what he tells you is you are to consider the alphabet to be the lowercase letters A through Z. Okay. So that means there are only 26 possible characters and there are 26 squared possible ways of arranging them. So you could imagine that if you said, oh, I've got an A here, and I've got an A here, and then a B here, and a C here, and a B here, and a C here, and it goes on up to Z for both of them. And each of these is an entry AA, AB, AC, etc., etc. You would have 26 possible combinations. In fact, if I just leave that there, we can see that we would get BB and CC, and then in the end, we would get ZZ. So, there might be 26 squared possible combinations, but of them, only this diagonal create the combinations that we want, a palindrome. And there are 26 of those. So the probability is 26 divided by 26 squared for 2-letter word palindromes. So we'll leave that up here again in a nice blue colour. So 1 over 26. 2-word. What about for 3-word palindromes? Well, in this case, how many combinations do you think there are? 26 cubed. Okay. Now, how many palindromes are there? Well, a palindrome would have to be the same forward as it is backwards. So say, for example, we've got this A question mark A. How many times can this style of palindrome occur? What could the question mark be? So the question mark could be A, could be B, could be C, could be D, could be all the way up to Z, right? Okay. So in that case, there's actually 26 possible A question mark A palindromes for 3-letter words. And it's the same for all of them. So in the end, I'd have a 26Z question mark Z palindrome. So actually, there are 26 times 26 possible 3-letter word palindromes. And so if we move this over here, then we can see that actually what we have is 26 squared possible 3-letter word palindromes divided by 26 cubed possible 3-letter word combinations. And this is also equal to 1 over 26. So perhaps counterintuitively, the answer to this one is equals. So thank you very much. I hope you liked this tutorial. Let me know what you thought of it, and let me know if there are any other parts of Stat 110 that you'd like me to cover, or if there was anything that was unclear that you think would benefit from a dedicated video. Thank you very much, and good luck with Stat 110.